Now, what we were doing was just doing some, reviewing some mathematical tools that we will be using, like the gradient operator, curl, divergence, and we did discuss to some extent the various coordinate systems. If I'm not wrong, we had usually we, up to now, we are used to using the Cartesian coordinates, but we will be using spherical coordinates or cylindrical coordinates. We will see what simplifications they will bring. And we had also discussed the Dirac delta function. So it was this weird function which was zero almost everywhere, infinite at a single point, but its integral over that point is 1. And using this Dirac delta function, we will be able to describe, for example, point charges. When we call a charge, well, we will be talking about the density, charge densities. Well, let's start with the charge density, what we mean by a charge density. We will be kind of mixing the order of subjects. Charge density. We will be denoting it by rho, and what we will do is we will define this charge density at the point R by, let's say this is the position vector. We will be looking at the density of charges at that point. We will just imagine a very small cube at that point, and this cube will have some charge delta Q and volume delta V, and the charge density is nothing but this ratio delta Q over delta V in the limit as delta V goes to 1. Now if we have a point charge, just a point, a charge at a point, then delta Q will be equal to Q independent of V. So no matter how small the volume we take, well, there is this point inside this volume, and hence this point has a charge Q. So delta Q, which is the charge inside the volume, is always Q fixed. But delta V goes to 0. So that basically tells us that rho of R at that point is infinite. In any other point, rho of R will be 0. There is no charge in any other point. So it looks like the Dirac delta. Furthermore, if you note that the Q total is equal to rho of R dV integrated over all space. So if you have this point charge, its density, charge density will be 0 everywhere except on that point. Furthermore, the total charge is equal to Q. So the integral of the density should be just Q. Or let me just call this rho 0. So rho of R basically satisfies all the properties of the Dirac delta. It is 0 everywhere except on a single point. Its integral over a region that contains that point is finite, and it is given by Q. If we are in 3 dimensions, this will be the density corresponding to a unit charge. So that is why we need these Dirac delta function. Now, let's start with the fundamentals of electric field and electric force. If you have 2 of these charges, Q1 and Q2, and then we know that they exert forces on each other, and the force will be proportional to the product of the charges, inversely proportional to the separation between the two squared, the square of the distance between the two, and it is along the line connecting the two. And it is with a proportionality constant. Let's say this is the force acting on 1 due to the charge 2. So this will be, Yep, it's unit vector. Okay, so the quantity is relevant quantity. This is acting on the charge 1. So it will be along this line. This is R12 hat. This distance is what we call the R12. And K is just some kind of a constant. What is this constant depends on which units you are using. So for example, in Gaussian units, the units that you are probably used to up to this point. No, in SI units, sorry. The unit of charge is Coulomb, and this K is equal to 1 over 4 pi epsilon 0. Epsilon 0 being the permittivity of space. It has some numerical value. Its unit is Coulomb squared divided by meters squared Newton. This is the unit of epsilon 0. But why do we choose? I mean, the problem is how do you define the Coulomb? Of course, you define the Coulomb in terms of the ampere. 1 Coulomb is defined as 1 ampere second. This is the definition of 1 Coulomb. But then the question is, what is 1 ampere? Now, the way we define the ampere is you just take two wires carrying identical charges, 1 meter long, and if the force, if you send a current through them, if the force exerted on each other is 1 Newton, then that current is what we call 1 ampere. But it is still kind of arbitrary definition. Why 1 meter of charge? Why 1 meter of separation? Why the 1 second? The alternative unit is the Gaussian units. Well, in Gaussian units, K is just 1. Well, kind of nice. At least it simplifies the notation. Then the unit of the charge is no longer Coulomb. What's the unit of charge in this unit? Well, you see the force is equal to, or the magnitude, Q1, Q2 divided by R squared. So the units of both sides should be equal. So the charge of unit in this, the unit of charge in this system is nothing but Newton to the 1/2 times meter. So if you just put, instead of, if you calculate the unit of the right-hand side is the charge squared, which is Newton meter squared, divided by the distance squared, which has the units of meter squared, so the right-hand side is just newtons. So the left-hand side is again newtons. This is just a different way of measuring the charge. Well, let us separate the charges in different units by putting a star over here. Then Q star, if you want to just switch back and forth between different units, Q star would be just 1 over square root of 4 pi epsilon 0 Q in the standard units. So you can easily go back and forth between the charges. Well, in CGS, the unit of Q, which we said this is Newton 1/2 times meter, this is also given a name, stat coulomb. It's just a different way of defining your units. Yeah. If you just change your units, you are just changing this constant K. So you can just, whatever convention you choose, as long as you are consistent, things will be fine. Well, there's another unit system that is commonly used. I'm used to this one. So-called natural units, in which K is equal to 1 over 4 pi. And in this units, C is equal to 1, H bar is equal to 1, etc. Well, what you are actually doing is, you see, when we are using the units, the standard units that we are using is 1 meter, 1 second, and 1 kilogram. Kind of nature doesn't care with what we call a length of this size. It's not a natural unit, 1 meter. Similarly, 1 kilogram is not a natural unit, or 1 second is not a natural unit. Well, it is natural for our sizes. 1 meter is nothing but the length of an arm. That's why we use the 1 meter unit system. 1 second, well, order of magnitude, let's say, it is the period of the oscillation of your leg. Order of magnitude, not the numerical value, but the order of magnitude. So that's why we use the 1 second, 1 meter, but that is for our size, not for nature. So in natural units, if you choose suitable units for time and length, then the speed of light just turns out to be 1 because that is the natural speed in nature. And h bar is the natural angular momentum in nature, and that is also 1. You measure everything in terms of multiples of these quantities. Well, in the book, we will be using this unit system. Have you ever wondered why we have this 1 over r squared law? You see, if you think of gravity, gravity is 1 over r squared. If you think of electromagnetic theory, it is 1 over r squared. And these two laws, as far as we know, they don't have anything in common. We did have attempts to unify them, but they all failed. Einstein was working on unifying these two. And we are still working on whether we can unify these two, but they don't seem to be related at all. Nevertheless, they still look the same. Why? What is this surface of a sphere? Well, so you see you have your 4 pi, and you also have the r squared in 1 over 4 pi r squared law, both in gravity and also in electromagnetism. Then the question is, how is the surface area of a sphere related to these force laws?
So the flux of the vector is through the surface area of the sphere, the constant, regardless of its value.
Yeah, in both electromagnetism and also in gravity. Basically, that's the idea. But in modern understanding, you should already know, you are listening to all these particle physics talks. Well, our current understanding of a force, whatever force it is just an exchange of particles. So if you are a charge, if you consider two charges, they are exerting a force on each other because they are constantly exchanging photons. Photons carry momentum. So if these two charges exchange a photon, they change their momentum. And if you remember Newton's second law just states that force is just the rate of change of the momentum. So whatever causes a momentum change, we observe it as a force. So in the case of electromagnetism, it is an exchange of these particles that we call the photons. They exchange momentum. They transfer momentum from one charge to the other one. So their momentum changes the momentum of the charges. So although we do not observe the photon themselves, we do observe their effect in the form of a change in the momentum of the particles. So if he is a charge, I am a charge, what we do is I am constantly emitting photons. He is also constantly emitting and also absorbing photons. If he is nearby, he will be absorbing some of the photons that I emit. So I constantly emit photons around. So if he is there, he will be seeing these photons. He will not be able to distinguish whether those photons are coming from me or the photons that he had himself emitted. So he will be absorbing the photons themselves that came from me. The amount of photons that he will absorb will be proportional to the density of photons at his position. Where the photons, after I emit them, they are moving at the speed of light in every direction. So they are basically spreading over the surface of a sphere in 3 dimensions. So the density of photons that reaches him decreases as the surface area of the sphere. And since we are living in a 3-dimensional space, the density decreases as 1 over r squared. So that's why in electromagnetism we have this 1 over r squared behavior. And we believe that for gravity also there's a similar mechanism, although we don't have a proof, neither experimental nor theoretical proof yet. We believe that there is what we call the graviton is being exchanged between particles, creating this force, and the same idea that the gravitons, they spread over the surface of the sphere, so the density of the gravitons reaching him from me decreases as 1 over r squared, and hence there is the gravitational force is also 1 over r squared law, at least at larger separations, at weak fields. But of course, there is the problem. Let's say I am constantly emitting photons, which we say that are carrying momentum. But if they are carrying momentum, they are also carrying energy. But we have energy conservation. If I'm an electron, I'm at rest. If I'm constantly emitting photons, my energy should remain the same at the same time. So how come I'm emitting photons? I mean, a photon at rest just stays at rest. An electron at rest stays at rest if there are no other electrons, no other charges around. But I said that I'm constantly emitting photons. Now remember your quantum physics or quantum modern physics courses. Is energy conserved? Let's start with that one.
The system is closed.
Mm-hmm.
The energy is conserved.
Is it? You see, there is an uncertainty relation, not just between position and coordinate. There is a second uncertainty relation in energy. Do you remember it? The uncertainty in energy times the uncertainty in time. Well, this is slightly different than the uncertainty relation in energy momentum. So there is no strict larger than or equality sign. So what this basically tells me that energy is conserved. If energy is conserved, we are basically saying that delta E is equal to 0. But if delta E is equal to 0, then delta T should be infinite. So to test energy conservation, strict energy conservation, we need infinite time. We cannot just test energy conservation in very short amounts of time. Well, this basically tells me that we can violate energy conservation as long as that violation lasts very short. In a very short amount of time, that violation of energy should disappear. Now, when I said that I'm constantly emitting photons, I'm constantly emitting photons and reabsorbing them. So there's, if we could measure my energy instantaneously, continuously, then of course I would see violation of energy conservation. But since I'm not making constant measurements, I'm just making a measurement now, a measurement then, a measurement then, a measurement then, etc. What I will see, I will still observe some fluctuations. These are classical fluctuations above the quantum fluctuations in the energy. On the average, I will still observe energy conservation. But nevertheless, in the intermediate steps, energy can be violated. And a large energy violation should last a very small amount of time. If delta E is large, delta T should be very small. Now let's come to another fact. What is the mass of the photon? What is the mass of a particle, let's say, any particle? Momentum over speed, that is one definition. Well, basically, if you remember the relativistic energy relation, remember C is equal to 1. You see, the mass of a particle is the minimum energy it has. So, for example, if I'm emitting a W boson, whose mass is like 80 times the mass of a proton, that is the minimum energy it will have. But that means delta E is huge. Such an energy conservation violation should last a very small amount of time. But in that very small amount of time, the W boson cannot really go far. It can only travel a very small distance. So that basically tells me that the W boson, the force carried by the W boson, which we call the weak force, acts only at very short distances. If you look at the mass of the photon, on the other hand, what is the mass of the photon? 0, as far as we know, both theoretically and the measured limits are very small, by the order of 10 to the power minus 31 kilograms, if not better. The photon is massless. So if I constantly emit photons, I can emit photons that have a very small amount of energy. And for these very small amounts of energy, delta E will be very small. If delta E is very small, delta T will be very large. But if delta T is very large, in that large amount of time, the photon can travel a large distance, as long as it has a very small amount of energy. Well, that means the electromagnetic force can reach very far distances. But of course, at very large distances, the amount of energy transferred will be very small. Now, that is basically the amount of momentum transferred will be very small, so at large distances, the electromagnetic force is weak. It can go large distances, but at large distances, it will be weak. So in a sense, everything is kind of consistent. Now, if the photon had a mass, we know that the force will be proportional to, well, for massless photons, we know that it's Q1 times Q2 over R squared. And if the photon had a mass, it cannot go very far. It will be suppressed at long distances. So this would have been the dependence. It will be exponentially suppressed. In fact, this is one of the methods that we are using to measure the mass of the photon. Is the electromagnetic force 1 over R squared, or is there an additional exponential suppression? Again, units, h bar is equal to 1 is equal to c. So anyway, let's go back to electromagnetic force. If we had these two charges, Q1, Q2, we said that the force acting on charge 1 will be equal to, let us also write it in a different form. Let's say this is R1, this is R2, these two vectors. This is equal to Q1 times Q2 times R1 minus R2 divided by R1 minus R2, the length Q. Now this time it is cubed because the numerator is not a unit vector. So this will be the force law that we will be using. Now, rather than the force, we usually define a quantity that we call the electric field. Because one thing that we don't like about this expression is that it looks as if the charge Q2 is acting the charge Q1 at a distance without any other influence. So what we will do is we will just call this one Q1 times E, the electric field at the point R1, where we define the electric field at the point R. We just put some test charge at the point R. Let's call it, it will feel a force. We just call it F of Q divided by Q, and then take the limit Q goes to 0. So what we do is, if you want to determine the electric field, let's say at this point, you just put some charge over there, a very small charge. It has to be very small because if you put a large charge, it will just change the configuration of other charges. We don't want that. We don't want to influence the other charges. The other charges should stay where they are. So we put a very, very small amount of charge. And eventually we take the limit as Q goes to 0. Well, of course, this is mathematically we can do it. Physically we cannot do it. But the idea is just put there a charge that is so small that it will not influence the other charges. And then you put the charge over there, you measure the force acting on that charge, divide by the charge. We know that the force felt by any charge is proportional to its charge. If we divide by the charge that we put there, the test charge, then this, what remains depends only on the properties of the other charges. And that quantity is what we call the electric field. So with this definition, the force felt by the first charge, I had already written it over here. So the force felt by the first charge is nothing but the charge of the charge that we put there multiplied by the electric field at that point. At this moment, this is just a kind of a change of terminology. It doesn't look as if we have gained anything at this moment. But conceptually now we are describing the force in terms of the properties of the space at a given point. So we put a charge at that point, and the force that that charge feels at that point is proportional to the electric field at that point. Then, of course, later on we will study, our main object of study will be this electric field, because once we determine the electric field, we know the forces. We know everything. Then we will study the electric field, and we will see that we will see that at any given point, if you put a charge over here, it just creates an electric field. First, it creates an electric field. And if we move that charge, the electric field in the near vicinity changes. Then the electric field in the further vicinity changes, etc. So in a sense, the change in the charge over here will be propagated by this electric field. So if we have these two charges, this charge over here creates an electric field over there, and that electric field exerts a force on our charge. Now, if we move this charge, then first the electric field here changes. That charge over there will not feel the change instantaneously. But this change in the electric field will propagate slowly meaning at a finite speed, at the speed of light. We will see that it propagates at the speed of light. And when that change reaches the other charge will feel that this charge has moved. So it's not that this charge instantaneously or over a distance influences the other charge. This charge only influences its near vicinity, but that near vicinity, the changes in the near vicinity also, this charge influences the electric field here. The change in this electric field here changes the electric field here. The change in the electric field here changes the electric field here, etc. And the other charge feels the change only after all these changes has propagated to it. So all the changes, all the influences in this field picture will be local. Everything only influences what is in its near vicinity. I cannot influence him. But what I do is I influence what is near me, and those things influence what is near them, etc. After this, let's say, chain influences, he will eventually feel the change. But that we will do towards the end of the semester. For the time being, we define this electric field. At the time being, it just looks as if just a change of terminology, but we will see that it has strong influences, important consequences, this new definition. Now, if we have a point charge, we already know that if we put some charge at some point R, a charge Q, let's say for a point charge, so the idea is the electric field created by a point charge, what we do is we put some charge, let's say large Q, at some point. To calculate the electric field, what we do is we put a very small charge Q at some other point. So this is our charge Q. We put here our test charge, small q. Then the force felt by this small q is nothing but Q times large Q divided by, let's say this is at the point R0, this is at the point R. We are looking for the electric field at the point R. So the force felt by this test charge, small q, will be just divided by R minus R0 cube times R minus R0. This is the force. The electric field is just limit as q goes to 0, f of q over q, which is nothing but large Q multiplied by R minus R0 divided by R minus R0 cube. This is the electric field of a single point charge. Of course, in general, we don't have a single charge. We have many charges distributed around. So let's say we have all these, let's call them Qi at the point Ri. So the electric field created by this system of charges is nothing but sum over all of them. The electric field at the point R. This is what we call the superposition principle. For electric field. Well, this is although it seems trivial, it's not always the case. Now, for example, in gravity, we cannot really write it in this form. If you have many masses, the total gravitational force acting on some test mass is not the sum of the forces exerted by each one of the masses. It doesn't always have this form. But in electromagnetism, it turns out that there is this property. In other forces in nature, electromagnetic theory has this property. Gravity doesn't exactly have it, but it is approximately true. In Newtonian gravity, this principle holds. But if you have black holes or objects that have a very strong gravitational field, the superposition principle does not hold. Neither in strong force nor in weak force. We don't have this superposition principle. But only in electromagnetic theory we have this superposition principle. And this superposition principle, furthermore, only holds for point charges. For example, if you have molecules, if you calculate the electromagnetic force that different molecules exert on each other, this principle still does not hold. Because you see, the problem with molecules is that, let's say you have one molecule over here, and it doesn't have to be a molecule, it can be any extended object, let's say. Let's take a simpler system. A conducting sphere. You put some positive charge over here. Now, you see, superposition principle in its strict form just tells you that the charge of the conducting sphere is 0. So first of all, the force should be 0. Well, it doesn't hold it that way because the conductor has many charges which move around. So if they move around, there will be some negative charges accumulating here. Positive charges will be accumulating on the opposite side. Well, the negative charges and positive charges, although they are in equal amounts, the negative charges are closer to the positive test charge. So the test charge will feel a force in this direction. So let's call it F1. Well, let's imagine the other case. No, we don't have that one. But let's imagine we put some other test charge over here. Sorry, let me remove this sphere. And my plus Q charge is still here. Then plus Q charge will feel a force, F2. And then we can just combine these two. We have our sphere. We have this test charge plus Q. Then plus Q prime is over here. Then this plus Q charge will feel some force F. And F, now let me see, this is, yes. F will not be equal to F1 plus F2. You see, if you go back to the superposition principle, here we wrote it for the electric fields, but if you would consider it for a test charge, just multiply it by Q. Now, Q times EI is nothing but the force exerted on our test charge due to the charge Qi, in the absence of all the other charges. And then we just sum them up to obtain the total force. Now here we did the same thing. F1 is the force that this plus Q charge feels in the presence of the sphere only. F2 is the force that this plus Q charge feels in the presence of only the plus Q prime charge. And when we put both of the sphere and the plus Q prime charge together, then plus Q charge will feel a force which is not the sum of the other two. So this is kind of a breakdown of the superposition principle. Why? At least in this form, the superposition principle doesn't work.
But we should take one charge. We should take the charge at every point in space.
Okay.
Yeah, so when we take the sphere as a whole, we don't know the charge distribution.
Yeah. The key word is the charge distribution. The problem is F1 is determined by one charge distribution created by plus Q only. If we put the plus Q prime over there, the charge distribution in the sphere changes. It's not the same that created F1. So since that also changes, the force due to the sphere is no longer F1. It is some other force, which you will be able to evaluate eventually. So in that sense, since F1 has been modified now, you don't have, if you would calculate this F1 prime force, then of course you will get F is equal to F1 prime, but F2. But you see, the superposition principle tells you that the total force is the sum of the forces, pairwise forces, that object will feel in the absence of the other charges. So that breaks down. Yeah, in this case, it's trivial to understand why. It's not really in the nature of the electromagnetic force, but mainly in the fact that the sphere is an extended object. That's why the superposition principle fails. In the other forces like gravity, the superposition principle fails because the gravitational force is created by the energy, not the masses. So if you have two masses, let's say three masses, let's say him, me, and you, well, he will exert a force on you due to his mass energy mainly, if he's not moving. I will exert a force on you mainly due to my mass energy, but we also have a potential energy. That potential energy, if both of us are in the same place, that potential energy will also exert a gravitational force. So that's why the gravitational force that he will feel is not just the sum of the forces that we exert separately. So that is why in gravity it fails. And in strong force and in weak forces, it also fails, this superposition principle. But we are in electromagnetism. It's nice, it behaves nicely. Superposition principle holds. And the electric field of a charge distribution at the point R, we said this is equal to Qi times R minus Ri divided by the magnitude squared cube. Well, if you don't have these point charges, but rather almost a continuous charge distribution, we can convert this to an integral. This will be just, well, you see, the way we convert it, suppose you have a charge distribution, you divide this into very small cubes, each one having a charge Qi, these cubes. Well, these cubes, they behave like a point charge, so we can use the summation. But we will be replacing this Qi by the densities, rho at Ri, times delta V. And when we take the limit that these cubes become infinitesimally small, almost point-like, that summation just becomes an integration. So instead of Ri, I will just use the symbol R prime. So this will be rho of R prime multiplied by R minus R prime divided by R minus R prime magnitude cube integrated over the volume. This is the electric field at a point R. Now, of course, we recover the previous expression if our charge distribution is just a collection of point charges. In the case of a collection of point charges, the density, we already said that for a single point charge, it's the Dirac delta function. If we have just a collection of charges, so it's just the density is just the sum of the charge distribution of all of them. This is for a system of point charges. So in this expression, you basically can go in both directions. So if you have a summation, you can convert it into an integration. And if you have an integration, a continuous charge distribution, if you know the expression for the electric field of a continuous charge distribution, you can just obtain the electric field corresponding to point charges. So they are basically equivalent. Any questions up to this point? Let's do one more step and then we can go for a break. Well, on last week, if you remember, we had shown that gradient of 1 over r is equal to, do you remember?
What's your domain? What's your domain?
Yeah, the gradient everywhere. Let's say r not equal to 0. Well, it should be something like 1 over r squared, right? So we are taking the derivative of 1 over r. It should be minus 1 over r squared, in fact. But it should be a vector. So which direction it will be? What's the most natural direction for this one? Radial. So it will be minus 1 over r squared in the radial direction. This is the gradient of 1 over r. Let's take the gradient of r minus r prime. We are taking the gradient with respect to r. Yeah, basically we are shifting the origin. So it will still be the same expression with a shifted origin. This will be minus r prime divided by r minus r prime cubed. Well, we know the electric field. We had written the electric field at the point r. This is equal to rho of r minus r prime, no, rho of r prime, the density at r prime, divided by r minus r prime cubed dv, integration over the volume. So we can write that thing as a gradient with respect to the coordinate r. Minus rho of r prime, gradient with respect to r, of 1 over r minus r prime. Well, that gradient with respect to r is nothing but derivatives with respect to the r, theta, and phi. They are not derivatives with respect to the r prime. Since it is that gradient is independent of r prime, I can just take it out of the integral. Well, the nice thing about this expression is that rho is just a number. 1 over r minus r prime is just a number, so the parenthesis is just a scalar expression, a scalar function, which we will call the phi at the point r. This is the electrostatic potential. So although the electric field is a vector, you see a vector has both the information on the magnitude and the direction, we can still express the electric field in terms of a scalar function, which only has information about the magnitude, using the gradient. So at least in electrostatics, we can always write the electric field as the gradient of some function. Now, what about the curl of this electric field then? We had studied various second derivatives. You see, this is equal to minus the curl of the gradient of phi. It is 0. Curl of the electric field is always 0 in electrostatics. And we will see that when we study moving charges, when we are doing electrodynamics, this will not hold anymore, but in electrostatics, the curl of the electric field is always 0. Well, what this basically means is that just consider the electric field over any closed loop, the integral of the electric field over any closed loop. We already know how to express this as an area integral. This will be equal to the curl of the electric field integrated over the surface bounded by this closed loop, but we know that the curl is 0, so this is equal to 0. So in electrostatics, the integral of the electric field around any closed loop is always 0. Well, that is the definition of the curl, in fact. If you take any vector field, E can be the electric field or any other vector field, that electric field integrated over a closed loop, it should be a closed loop, it is always equal to the curl of that vector field integrated over the surface bounded by that loop. Well, in fact, this is analogous to this one. You see, A and B are the boundaries of this line. So the integral over the boundary is always equal to the integral over the interval of the derivative. So curl is essentially the derivative of the electric field. So we have on the left-hand side, we have the integral over the boundary, which is the closed loop. On the right-hand side, we have the integral over the interior of the derivative. We also have one more thing with the divergence. That is for the volume. E dot ds, this was, okay, if we have a closed surface, this is the integral of the boundary of the volume. This is equal to the integral of the divergence of the electric field. This is the derivative of the electric field over the volume. And that we will study at the beginning of the next hour. Now, before you go, you see there's a problem though in this expression. Let's also clarify that E dot dl is equal to curl of E dot ds. Now, kind of dl is easy to understand. It's a vector. So we have this closed loop. We have to go around this loop in some direction, and that direction gives us the direction of dl. So if you just imagine this very small segment over here, this is the direction of dl. What about ds? What is ds? Perpendicular to what? Perpendicular to dl. Well, you see, dl is just this line. This is perpendicular. All of these vectors are perpendicular to dl. Perpendicular to the surface. ds is perpendicular to the surface. But still we have a problem. We have two different perpendiculars. So if this is your surface, this is perpendicular, this is perpendicular.
Direction to increase. Increasing direction. Direction of the
What is increasing?
gradient is positive. Gradient is positive.
Gradient is a vector, so it cannot be positive or negative.
Direction of the
Direction of dl. ds is in the direction of dl. Well, if this is dl, this is the direction of dl.
So right hand rule.
Yes, the right-hand rule. Remember the right-hand rule. And also don't forget that when we are evaluating these integrals, we are dividing our segment into very small, the area, let's say, into very small bits, eventually taking the limit that it goes to 0, the sizes. So even if we have a curved surface, each one of these very small segments, surface elements, is very small. Since it's very small, it is almost flat. So there is two perpendicular directions to that surface. There's no ambiguity in that. And the direction you determine by the right-hand rule. For example, in this case, since the loop is going like this, in this sense, in the counterclockwise sense, if you use the right-hand rule, that is, curl your fingers, 4 fingers in the direction of the loop, then your thumb points in the direction of ds. So that uniquely defines ds. So here, for example, ds is in this direction. That is the direction of ds. Of course, the surface can be curved, let's say. Okay, this is a valid surface. Let's say the loop is in this direction. The ds is somewhat in that direction by the right-hand rule. So here it is in that direction, here it is in this direction. It constantly changes continuously changes with your surface. So that is why we have to divide our surface into very small bits, and those very small bits are almost flat in the limit that we take those infinitesimal surface elements to have 0 area. They will be flat. Since they are flat, the direction of ds for that infinitesimal patch is unique, given by the right-hand rule. And you have to change it continuously. So only with these conventions of the direction of ds and dl, that first line is correct. Because if you change the direction of ds, there's a minus sign. Okay? Just to keep in mind. Okay, any questions before the break? Okay, so see you after 10 minutes.